Hi, I'm Quinn, and today we're unpacking quantum probability, one concept at a time. Let's talk about a phrase that sounds harmless but is deeply wrong. Quantum probability is just classical probability with extra randomness. Quantum probability isn't classical probability, because quantum mechanics doesn't assign probabilities directly to which outcome is true. Instead, it assigns amplitudes, and amplitudes can have phase. Here's the one-line math that changes everything. If two alternatives contribute amplitudes A and B, the probability is the squared magnitude. A plus B squared. When you expand it, you get H squared plus B squared plus an extra piece, an interference term. That extra term can be positive or negative. It can boost an outcome above the classical sum, or cancel it down toward zero. Classical probability can't do that. If A and B are mutually exclusive, classical probability insists that PA or B is PA plus PB. No bonus term. No cancellation term. Now here's the operational twist that makes this feel real instead of abstract. Whether you see interference depends on whether you measure the alternatives. If you perform a which path measurement, basically checking which alternative happened, you destroy the coherence between the alternatives. And once coherence is gone, the interference term disappears and probabilities behave more classically. So in quantum mechanics, inserting a measurement in the middle isn't just collecting information. It changes the state and it changes the probability accounting. This is why people say quantum probabilities can violate the classical law of total probability. Often what they mean is, the probability of the final outcome depends on whether an intermediate measurement was performed, even if you never look at the intermediate result. And under the hood, there's an even deeper reason. Quantum events don't form the same kind of logical structure as classical events. In classical probability, events behave like sets with normal and or logic. In quantum theory, events correspond to subspaces or projectors, and the logic is non-Boolean, especially when measurements don't commute. The Stanford Encyclopedia describes quantum mechanics as a non-classical probability calculus resting on non-classical logic. Let's also explore one of the weirdest concepts in quantum computing: the difference between probabilities and amplitudes. Imagine you're at a music festival with two stages. You want to get to the beer tent, which is right between them. Now, in the classical world, the world of regular probabilities, here's what happens. You flip a coin. Heads. You walk past stage 1. Tails. You walk past stage 2. Either way, you end up at the beer tent. Simple, right? The probability you arrive at the beer tent is 50% from path 1, plus 50% from path 2. Total, 100%. You're definitely getting that beer. But in the quantum world, instead of probabilities, we have amplitudes. Think of amplitudes like sound waves from those two stages. Stage 1 is blasting music. That's amplitude from path 1. Stage 2 is also blasting music. That's amplitude from path 2. Now here's the kicker. When you're standing at the beer tent, you don't just add the volumes together like you add probabilities. The sound waves interfere with each other. If both speakers are playing in sync, the same frequency, same phase, the waves constructively interfere. They amplify each other. The music gets louder. This is like getting a probability greater than what you'd expect from just adding. But this is the quantum magic. If the speakers are perfectly out of phase, the sound waves cancel each other out. Total silence. In quantum terms, you could have two paths to the same outcome and they cancel each other, giving you zero probability of that outcome happening. In classical probability, two ways to reach the same result means it's more likely. In quantum mechanics, two paths can cancel each other out, making that result impossible. Here's the technical bit. Amplitudes are complex numbers. They have both a magnitude and a phase, like how sound waves have volume and timing. When you want the actual probability, you square the amplitude. It's like asking, how loud is the combined sound? You measure the intensity of the wave. So the recipe is 1. Add the amplitudes, let the waves interfere. 2. Then square to get probability. Not the other way around. And this is why quantum computers are powerful. Classical computers? They're like flipping coins and adding probabilities. Quantum computers? They're like conducting an orchestra of interfering waves. We can choreograph which paths amplify each other and which cancel out, steering the system toward the right answer while making wrong answers destructively interfere into silence. So remember, probabilities are like adding volumes. Amplitudes are like adding waves, and waves can cancel. That's the quantum difference. If you're learning quantum computing, here's the practical takeaway. Quantum algorithms are powerful not because they try everything, but because they use phase to create interference, making some outcomes cancel and others build up. So when you hear quantum probability, translate it to probability that comes from squaring amplitudes, where phase and measurement context matter. That's not classical probability with glitter. It's a different rulebook. That's all for today. Take care.